Great. Thank you very much for inviting me to this very fun conference. I want to speak about gravitational wave detection at the microhertz frequencies. So what's the plot here? Well, we've detected gravitational waves, right? LIGO saw gravitational waves at kilohertz frequencies, 40 hertz to kilohertz. And more recently, as all of you are probably aware, the nanograv collaboration using pulsar timing arrays, they saw gravitational waves around a nanohertz or so. And I believe in continuity in physics, which clearly means there should be gravitational waves all the way here. And it's important to go and look after them, to go look at them, simply because it's just like electromagnetism, right? We have seen the electromagnetic spectrum, we've started the telescopes, optical telescopes, and we have now built gamma ray telescopes, X-ray telescopes, radio telescopes, all kinds of things. And the universe has given us interesting things to understand through this entire spectrum of electromagnetic waves. And I think there's no reason why the gravitational wave sky would not be similarly exciting. And in electromagnetism, we had to build different kinds of instruments, different kinds of technologies to span the full spectrum of possibilities. And this is very likely true in the gravitational wave story also, where you're going to need different kinds of technologies to go after this huge range of frequencies between where nanograv is today and where LIGO has already seen gravitational waves. And in this vast set of frequencies in the middle, there are existing experimental attempts to go after gravitational waves. As you know, there's a LISA experiment that is looking for gravitational waves around millihertz or so. Lots of effort going on in that direction, and hopefully it will be approved and it will fly. Some people have also pushed for atom interferometers to look for gravitational waves in the, let's call it a tenth of a hertz to about 10 hertz or so. And what I'm interested in today is basically what about between nanograv, which is around, let's say, 10 to the minus 8 hertz, to about roughly where LISA cuts off, around 0.1 millihertz or so. What about gravitational waves in that region? What might one want to do to go and look for those things? So if you think about this issue, right, this plot has something already very interesting, where if you look at the characteristic strain of the gravitational wave, and that is the amplitude of the gravitational wave that you want to look at versus frequency, what you see is this. For LIGO, they had to go and detect gravitational waves with a strain of around 10 to the minus 22, whereas for nanograv, the strain is something like 10 to the minus 16 or 10 to the minus 15, right? Orders and orders of magnitude larger than what LIGO is trying to go after. Why is that? That's due to the fundamental physics. LIGO is looking for mergers of 10 solar mass black holes or neutron star binaries, things of this kind. These guys are somewhat small, and so the gravitational waves they produce have somewhat lower strain. While at very, very low frequencies like this, you are looking at the mergers of supermassive black holes. Those are extremely big, and so they are intrinsically much brighter than the gravitational waves that LIGO is looking at. So as you lie on this plot, you basically see an interesting fact, which is that as you look for gravitational waves at lower frequencies, simply because you're looking for much more violent events, the intrinsic strain that you are trying to go after is better and better and better. It's bigger and bigger and bigger, right? So what's the challenge in this story? Well, the challenge is the following. As you go to high frequency, okay, you need very, very precise instruments because the effects are intrinsically much smaller. Whereas at low frequency, the size of the amplitude is considerably bigger, but the real challenge is stability, right? If you're looking for, say, what nanograv was trying to do, which is look for gravitational waves at nanohertz frequencies, you fundamentally need instruments that remain stable over years. And that's also a different kind of challenge. So at microhertz also, you'll have similar kinds of challenges, and these are two ideas and thoughts on how one might combat them. So first, I'll talk about how one might look for gravitational waves from about a microhertz to about 0.1 millihertz or so through some kind of asteroid ranging. That's the first part of the talk. And part number two will talk about how one might use astrometry to look for gravitational waves from about 10 nanohertz to about a microhertz. All right, asteroid ranging. What's the idea? Well, here is the basic plot on how you want to look for gravitational waves. A gravitational wave comes by, it causes the distance between two objects to modulate, and if you can measure the modulation of this distance, you're basically done. So the LISA experiment, for example, looks for the fact that a gravitational wave will go by and it causes the distance between these two satellites, or really proof masses that are inside these satellites, to modulate, and that is what they're trying to measure very precisely with an optical interferometer. The challenge is the following, right? This satellite has all kinds of stuff with it, and even though you're in space, random things will happen to the satellite, outgassing, stuff hitting it, whatever it is, that causes the satellite's position to wiggle a little bit. And as the position of the satellite wiggles, it will gravitationally couple to the proof mass, and you can't do anything about that, and that will therefore cause some sort of transfer of environmental perturbations of various kinds onto the proof mass. And you have to engineer your satellite so that you're basically flying in what's called a drag-free form, so that the random motions of the satellite don't really couple to your proof mass. And this is a very challenging problem, and the LISA Pathfinder mission basically accomplished that goal for LISA frequencies. So these are wonderful results for the LISA Pathfinder collaboration. It took them many years to get there. And indeed, what they have demonstrated is basically that, this noise curve is real data. They've basically demonstrated that if you want to hit the performance levels necessary for LISA, that is now actually possible. In fact, they did a little bit better than what was necessary for LISA. But this is a noise curve that you actually have. And what you see is this, right? At LISA frequencies are exactly where they want to be, but at frequencies below LISA, of course, their noise goes up. And that's a very generic thing, where at low frequency, things go bad, simply because of the fact that if you're interested in position fluctuation, which is basically what your gravitational wave is ultimately causing, you notice that even a small acceleration can cause a much larger displacement at low frequency, simply because an acceleration becomes a displacement as 1/2 AT squared, and at low frequency, you have more time for that to build up, okay? So if you put in the numbers and you basically say, look, think about some kind of LISA style experiment where I've got two satellites, they're separated by something like 1 AU, and let me just simply use LISA Pathfinder numbers and ask, well, can LISA-like technology, current day LISA-like technology, see gravitational waves? The answer is no. The Pathfinder needs to be better by maybe about 2 to 3 orders of magnitude in order for it to really see interesting gravitational waves. Now, it's perfectly possible that people improve on LISA Pathfinder and achieve those 2 to 3 orders of magnitude. Okay, that's perfectly possible. But I think it's interesting to ask, could one do something a little bit different? I'm a theorist, and when I teach freshmen, I say, look, the dumbest way in which you can suppress acceleration is by the fact that I have A is F over M. And so if I have an object that is very big, the same force will cause a small acceleration. But I can't really launch very, very heavy things into space. That's extremely expensive. So what could you do instead? So instead of trying to look for the distance between two satellites, where the fact that the satellite masses are about 1,000 kilograms or so gives rise to the performance numbers of LISA Pathfinder, let's think about large natural objects. Could you use a planet? Okay, the idea would be, could you measure the distance between two planets very accurately? Now, indeed, the center of mass of the Earth is an extremely stable object, right? It doesn't move that much. However, we can't really use the center of mass of we have no direct access to the center of mass of the Earth. What we have access to is the surface of the Earth. And the surface of the Earth is a very noisy thing. There's seismic noise, all the stuff that limits LIGO, right? Plus you have atmospheric problems, things of this kind. So one can't really use planets of this kind. But how about objects that are big enough that random motions are suppressed because they're huge masses? However, they're not so big that they have their own internal dynamics, right? So let's think about something like a few kilometer scale rock or an asteroid. These guys are small enough that there's no atmosphere bound to them. They're also small enough that if you look at the aeons of time, their internal heat of formation is kind of gone away, okay? It disperses away. And one might then therefore ask, well, could these kinds of rocks be good enough for us to do this kind of ranging, okay? Like a LISA style experiment. So here is the basic idea. We're imagining taking two asteroids and landing something on them, okay? And simply doing a radio or laser ranging experiment from one base station on one asteroid to the other. And the idea would be to basically have fancy atomic clocks that are located there, and all you're really doing is sending laser light or radio from one to the other, and you're simply measuring the time of arrival of these pulses from one to the other, and if a gravitational wave goes by, the distance will modulate, and you're using your local clock to see if the time of arrival is modulating at the frequency of interest. Does this idea make sense? So first, let's ask, what kind of numbers are we talking about, right? So at microhertz frequencies, to see expected sources of gravitational waves, you're thinking about strains of around 10 to the minus 17 to about 10 to the minus 18, okay? Considerably brighter than what LIGO is looking for. And if you have a 1 AU baseline between these two things, the length changes you're trying to measure are like 0.1 microns, right? So you only need the surface and the center of mass of the asteroid to be stable to 0.1 microns, right? Not the crazy LIGO number of 10 to the minus 18 meters. Okay, this is considerably larger than that. So baseline doesn't look completely insane. So let's now think about other possible things that could be, are they possible or not? Can we actually land things on asteroids? Humanity has in fact been sending robotic craft to asteroids now for over 2 decades. For a variety of technical reasons, apparently it's easier to go to asteroids than it is to go to a planet, because asteroids don't have large self-gravity. So if you go to a planet, the big thing is that you go to the planet and then you're supposed to slow down in order to land. And that's the final 5 minutes of terror or whatever that people talk about. With asteroids, the claim is that you launch yourself in a clever way so that when you get to the asteroid, the relative velocity between you and the asteroid is small enough. And then you kind of just gently park yourself on top of that. So both NASA as well as the Japanese Space Agency have sent a number of robotic craft to asteroids. So that part of it doesn't sound like it's nuts. Second, are there good enough atomic clocks? I am the worst person in this room to talk about that question when Jun and other people are over here. But indeed, you're talking about clocks that are stable to 1 part in 10 to the 17, 1 part in 10 to the 18. And those, of course, exist on the ground, though we don't have anything in space. Right? So at least at the level of the, theorist order of magnitude, this is not nuts. Then comes the real question. Is the asteroid center of mass and surface, are they stable enough? What do we know about these things? So we've gone through a number of possible noise sources. Some of them are known knowns. Okay, this includes things like the fact, things that will disturb the center of mass. So basically, I know that there are solar intensity and solar wind fluctuations. So these are measured, and you can basically ask if these things go and act on the asteroid, by how much do they actually move the center of mass? Okay, turns out if you have a few kilometer asteroid, the mass is big enough that these things are smaller than the 0.1 micron stability that I'm looking for. One can also look for torques caused by solar intensity and solar wind fluctuations. They're also basically comparable to the center of mass fluctuations that is caused by these things. Then we can think about other issues that people worry about. For example, there could be thermal cycling. So what is the thermal cycling? This comes from the fact that actually, your asteroid is pointed towards the sun for some time, then it rotates. So it goes from hot to cold very dramatically. And that can in fact cause seismic activity. So nobody has ever actually landed anything on an asteroid to measure the intrinsic seismic activity over there. Nobody's done that before, but people have done that on the moon. And a lot of our knowledge of exactly what might possibly be happening on the on the asteroid. I work a lot on axions as well. What might actually happen on an asteroid, lunar data. And what is true in the moon, at least, is that if you look at the kind of thermal quakes that are caused, they're more like at the nanometer level, right? So a factor of 100 or something smaller than the 0.1 microns that we're talking about. Okay. So we believe, having gone through a number of these kinds of estimates, that there are reasonable reasons to think that the surface of the asteroid should be stable out to 0.1 microns over this 10 to the second period. Okay. So yeah.
I did not understand the principle of the scheme that you are proposing. Because,
Yeah.
In the literature there are schemes where you use interferometer like clocks, but
Yeah.
you need a very sophisticated link to compare the clocks.
Yeah.
Maybe will not be in the microwave. Or there are proposals by Kolkowitz to measure the Doppler shift. So I don't understand, because you are talking about ranging.
Just timing, yeah. So basically what you need to do, right, is the fact that, like, in fact, there are a couple of things you could do, depending on how much laser power, etc. you have. So you could actually even, because, we're talking about like 0.1 microns over 10 to the 6 seconds. So you could even do something very dumb, like I have a laser on one that I shine, and the laser goes and hits a mirror on the other side, and it bounces back. Right? So you just simply, looking at, I sent this time pulse now, it goes and hits and comes back. Timing, okay? So we're doing something as, yeah.
Okay, but when you're talking about the, millimeter or whatever, micro unit is the distance, are you talking about, presumably you're talking about the center of mass of the asteroid?
Yeah.
So, and then how would that be defined? Because presumably...
I'm only looking at fluctuations of that, right?
Right.
So, yeah.
So do you want, and also presumably they also rotate?
Yes.
So do you want
Good. So these are great questions, right? So we haven't optimized necessarily for that. So one could indeed ask this question. The asteroids indeed, they rotate, they have a few hour period. And so there are two things you could, well, several things you could try to do, right? One is maybe you have more than one landing spots. This again turns out to be something that people have done, like you can land in multiple spots on an asteroid. That's one possibility. Or you could park yourself, you could put a little orbiter around the asteroid and, put something on the asteroid and use that as a proof mass essentially. Okay. But I even think that, what are we talking about, right? So these things are rotating. They have a few hour period. So even if I'm not always pointing towards the other guy, I will have some duty cycle loss, right? Where once, every few hours I'll have a link and then I make my measurements then. And the interesting thing about microhertz frequencies is that your signals live a very long time, right? So it's not like LIGO where you need to be looking at something every few seconds, otherwise it's gone. So you might, I'm not the one going to build any of this. I'm a theorist. I don't have the money for any of this, right? So whoever decides to do something like this, I think there are multiple kinds of possible things one could think about in terms of a trade space between the duty cycle that you want and how complicated it is to do either like multiple mirrors on the surface or simply have an orbiter that goes around.
I'm not as much worried about the mirrors as how those mirrors move relatively to the asteroid.
So you attach them to the asteroid, and see, the point is that as long as the asteroid surface is stable enough, right? That's all it is, right? Like you're rigidly attaching yourself to the rock.
So that's kind of my question. Like, are those asteroids actual rocks? Because
Good.
those are Osiris-Rex mission and strange things happen.
Absolutely, absolutely. Very good, very good. So it turns out, different kinds of asteroids. So there are stony asteroids. Those are the kinds that we want. So NASA did go to something called Eros 403, okay? And that is a stony rock. There are also other asteroids which are called rubble piles. That we don't want. The rubble piles are the ones where stuff happens. So what is the origin of the stuff? The origin of the stuff is that these rocks are weakly bound together. They may be attached by ice. And when the sun, does its thing, the ice will melt and do stuff, right? So indeed, there's a choice now of what kind of rock you want to go to. And what we would say is that find the stony rocks. Okay, that's the thing. All right. So from the order of magnitude stuff that we can talk about as theorists, we think there are reasons to think that asteroids might potentially be really nice proof masses for this kind of concept. And so what we would want to advocate for is that the next time someone goes to an asteroid, take a seismometer with you. Okay? Nobody's ever done seismometry in situ in an asteroid. And so what you want is an instrument that can land on the asteroid and ask if, maybe you put a couple of things on an asteroid and you ask, well, is the relative motion between two ends of this thing, is that less than 0.1 microns over 10 to the 6 seconds? If it happens to be true for a stony asteroid, you then have a candidate for where you could place something like this. Okay? Yes?
So sorry, I'm going to have to actually say questions at the end because we're almost at the end of the official time. So
okay, yeah, we'll talk about that stuff. Okay, great. That brings me to the next part of my talk, which is astrometry. And where does that come from? It comes from the fact that there are asteroids. So one thing that we asked is the following question, right? So what do I want to do? I want to take a couple of proof masses, and then I want to measure the distance between them. Now, whether this is actually, let's say, due to the asteroid ranging or it's even some LISA-style satellite, if you're inside the inner solar system, there are all these asteroids in the main belt going around. And these asteroids will go around, they're going to exert time-dependent gravitational forces on your proof masses. Okay, can't do anything about it. So in low frequencies on the Earth, we call that time-varying gravity gradient noise, Newtonian noise. So there's also Newtonian noise in space, and the Newtonian noise in space is coming from the fact that we have thousands of asteroids going around. Okay, so we went around estimating how big this is, and it turns out that the frequencies above microhertz is very small. One doesn't have to worry about it. But as you go to frequencies below microhertz, this rapidly becomes extremely important. Okay, and very quickly it actually becomes considerably bigger than the gravitational wave signal. So this is an estimate of how well we did that, and effectively it turns out that this noise is so big that is about a factor of 1,000 or something larger than what you would need in order to see gravitational waves in the inner, if you are using proof masses inside the inner solar system. Okay, time varying gravity gradient noise. So what could you do? Okay, just an interesting theoretical question. What can one ever do to go after this kind of signal? Well, if you look at it, the pulsar timing array guys, right, they saw gravitational waves by sitting on the Earth with all the seismic noise. How do they do that? Is because they're looking at proof masses that are intrinsically very far away. Because when your proof mass is intrinsically very far away, your signal in this case gets much more amplified than anything you can typically do in the inner solar system. So what one can therefore ask is basically, could you get a drastic boost in your signal, okay, whereas your noise is completely local? Can you improve your gravitational wave signal very much in a big way so that the signal to noise once again comes in your favor? And clearly it works for pulsar timing arrays. Well, why can't they get to higher frequencies? That's simply because of the fact in a pulsar timing array, right, the distance change you're looking for is the fact that a gravitational wave goes by, and you basically gain this strain out to a wavelength of the gravitational wave. So the wavelength of the gravitational wave is very, very large at low frequency. Your signal keeps increasing. But of course, once the gravitational wave's wavelength, okay, becomes small, this boost gets cut off. So pulsar timing arrays cannot go to higher frequencies. This is basically where their sensitivity lies. And I'm talking about something in this region. But why did pulsar timing arrays work? They work basically because pulsars are intrinsically nice, stable clocks at the astrophysical level. And so what they're really doing is the fact that a gravitational wave goes by, the distance between the Earth and the pulsar gets modulated, and you have really nice clocks on the surface, and you're using that to look for time of arrival modulations. So if I want to look at distant astrophysical objects to once again gain this magic, I have to ask, what are other stable aspects of distant astrophysical objects? What else can I look at? One option might be the center of mass position of stars. And so the question would be, can I measure the center of mass position of a star via some angle measurement, right? So what do I want to do? I want to look at one star and another star, and there's some angle theta between them. A gravitational wave goes by, that's going to cause the photon paths to change a little bit, and that will cause the angle between these two guys to fluctuate a little bit, right? So that's what happens. Your theta changes by an amount h. What's the challenge with this idea? The challenge with the idea is that for interesting gravitational waves, the strains you're looking at are 10 to the minus 15 to 10 to the minus 16. So you have to measure this angle very accurately. Not only do you have to measure the angle very accurately, it better be the case that the star's position is also sufficiently stable, right? You need a good proof mass. Just like how the pulsar was a good clock, you need stars whose center of mass positions are sufficiently stable. Now, even if the star's center of mass position happens to be sufficiently stable, what you're really looking at is not the center of mass directly, you're looking at the light, right? So what you actually measure is the photocenter of the star, right? Not the center of mass position directly. The problem with the photocenter is that stars have star spots. And when you have a star spot, there is going to be a fluctuation in brightness. And with the fluctuation in brightness, that will change the photocenter, even though it doesn't actually change the center of mass itself. So what you therefore have to ask is basically, at your frequencies of interest, is your photocenter sufficiently stable? Okay? Is that actually possible? Well, let's look at the formula for the photocenter. And the estimate here is that small r is some kind of size of some spot, some star spot that shows up. Capital R is the overall size of the star itself, and L is how far away the star is from the Earth. Okay? So that nice bit of formula basically tells you what is the angular fluctuation caused by a certain intensity fluctuation for an object of certain size r when it's a distance L from me. What you notice is that the smaller the object, okay, the larger the intensity fluctuation I can tolerate, simply because the overall object is small, right? So intrinsically I should be looking for small objects so that the photocenter doesn't wiggle too much. We looked at this for main sequence stars and the numbers don't look great. What about white dwarfs? Okay, that's the next size you can go to. And what's interesting about white dwarfs is the following, right? White dwarfs spin pretty rapidly, like every few hours or so. So let's imagine there's a photocenter, some kind of white dwarf spot, okay, that actually shows up in the white dwarf. And here I am on the Earth looking at this white dwarf. So if I actually have this this star spot appearing and disappearing, what we will see is that the intensity of the white dwarf will actually fluctuate just from a telescope that I'm looking at. Okay, and people have in fact done these measurements just to see what's going on in the world, and it turns out there's a whole collection of so-called non-magnetic white dwarfs whose intensity stability has been measured to be better than 10 to the minus 4. Okay, through the Kepler instrument, and they actually get a name. It's called the Landau standards, simply because the astro guys want intensity standards of this kind, right? So these things are known to be stable to at least 1 part in 10 to the 4, and in fact the limit on that stability is not that they actually saw the thing flicker, it is actually because their instrument short noise limited them in terms of how much exposure they had to actually measure it. So they could in principle be more stable than this. So the interesting thing is that now if you say I have a white dwarf which is about 10,000 kilometers in size and its intensity fluctuation is known to be better than 1 part in 10 to the 4, then if you want to detect gravitational waves with a strain of around 10 to the minus 16, that white dwarf should be around a kiloparsec or so away. Okay, that would make the intrinsic photometric fluctuations smaller than what we want. The other nice thing about white dwarfs is that you might also worry that the position of the star could actually fluctuate because of planets and rocks and things like that. But the cool thing about a white dwarf is that before you become a white dwarf, you become a red giant. And you become a red giant, your star expands out dramatically and eats up whatever is there in its inner regions. Okay, so something like, the sun becomes a red giant, I think all the way out to Mars or whatever is ultimately gone. So that will essentially do a nice job of clearing out the inner part of the orbit. Now this turns out not to be necessarily completely robust, because what can happen is that if your star actually has other planets or something at further away, those things can occasionally pull things inside the orbit. Okay, that's possible theoretically, but the astro people actually believe that very reasonably about at least half the white dwarfs you see should not have these kinds of issues. So white dwarfs have the fact that their photocenters are stable, center of mass also stable, because the red giant phase eats up whatever could be causing trouble. So what we would like to propose, therefore, as a thought experiment, is what does it take to do the astrometry of white dwarfs, right? So this is a rough theorist argument. You basically say, look, I'm going to put in numbers that I can make up so that I get the answer that I want. So roughly, you look at the known spectra of white dwarfs, and what you roughly need if you want to do h of around 10 to the minus 16, assuming the white dwarf is at about a kiloparsec, based upon the flux that you expect on the Earth, you would look at some kind of an interferometer, like a Michelson-Stellar interferometer, with a baseline of around 10 kilometers or so, in order for you to go and accomplish this task. Okay, and in fact, these numbers may become quote unquote easier if in fact someone actually bothers to go and measure the intensity of white dwarfs better, and you find out that it is actually stable to say 10 to the minus 6 instead of 10 to the minus 4, that would mean I can look at closer white dwarfs, and that would make the intensities numbers much better, so you don't need as big a baseline. Okay. Anyway, this is sort of the theoretical idea of what's interesting. And for me, the main point is this, right? That actually this kind of instrument was sort of proposed in the early 2000s. I'm not an instrument builder, so I cannot tell you how easy, hard, blah, blah. Definitely not easy, how hard it actually is, the level of hardness. But these kinds of instruments were proposed by folks at NASA in the early 2000s. And from what I understand, it was political considerations that made them go away from astrometry towards landing on the moon and stuff like that. I believe an instrument was even almost built, the Space Interferometry mission, for which $600 million was spent before it was canceled. Okay. So anyway, for me, the thing is that I think there's a great science case to do astrometry anyway, right? You can use these things to look at exoplanets. You can use these things, in fact, to understand more things about white dwarfs. But now, with things like nanograv, what you actually see is that there's a terrific science case just from gravitational waves to go and do astrometry like this. Okay. So with that, let me conclude. In my opinion, gravitational astronomy is here to stay. I mean, it's obviously the thing that we're going to be doing for the next 100 years in astronomy, I think. There's a very strong science case to probe the entire gravitational wave spectrum. And what I've argued to you today is that there's a strong case to think about asteroids as nice test masses in the microhertz frequency range. And our wish list right now, I think, is not so insane. It just basically asks, can someone who goes to an asteroid do a seismology measurement and see and prove that, in fact, the surface is stable to, 0.1 microns? And it also encourages development of space-qualified atomic clocks, which ultimately I think would be useful for things of this kind. And if you go to frequencies below about a microhertz or so, the gravity gradient noise from asteroids is very serious. It's orders of magnitude larger than what we need to see gravitational waves of interest. And so at that point, I think astrometry has this very, very interesting possibility where you say, look, we actually know, much like what we know about pulsars, right? For pulsars, we know they're stable clocks. And I would say white dwarfs are also known to be photometrically sufficiently stable. So it encourages missions of this kind as well. Thank you.
Mariana?
I have more questions.
Sure. Yeah.
So essentially you're saying that the idea is asteroids below microhertz or
That's
so,
right.
but it's fine for the higher
Correct.
frequencies.
Higher. Yeah.
So returning back to the issue of seismic activity.
Yeah.
One of the main sources of seismic activity in the moon principle, it's a micrometeorite hitting the moon.
We estimated that.
So presumably that would be the major source for asteroids. So I wonder if that can just be estimated for.
Yeah, we did estimate that, exactly.
Okay, so you approximately know, and that's okay.
That's okay. Yeah, so in the moon, actually, the biggest source of quakes are actually from the tides, tidal activity from the Earth. So the tide, so basically they see these huge, deep lunar quakes every 27 days. Okay, and so so the asteroids are both small and they're not really near any big planet of this kind. So the largest source of lunar quakes would not be there on an asteroid. So I think that the real thing that we worry about is basically like, the unknown, right? That there's basically some ice somewhere and it actually melts and does something like that.
And another question, if we consider various astrophysical bodies, you also have the orbits of exoplanets. I don't know how well they measure it. Would the gravitational waves affect orbits of the exoplanets or not?
Gravitational waves affecting exoplanets.
Orbits of the exoplanets, because presumably we can track them rotating, and some would rotate actually very fast because they're pretty close.
Yeah.
I just wonder if that's a potential.
Well, the thing is, anything of that kind, right? You're fundamentally just worried about the fact that this exoplanet itself is not stable, right? It's just like, why do we not look at anything in the solar system? It's simply because once it becomes too big, it has its own dynamics, and then it's troublesome.
Thank you.
Thanks. So the question about the last talk and astrometry, what you're asking is not only to resolve stars from very far distance, but it maintain very high stability of resolution, of angular resolution, to be able to detect the gravitational wave.
That's right.
So the key question is, what is your reference? Because we know mechanical structure is going to drift. So you talked a lot about making sure you find a stellar body that's stable.
Right.
But in fact, the problem will be on your receiving end. And so, are you thinking about something like put two artificial satellites as your artificial star nearby to just calibrate your angular resolution, make sure it's stable? Is that what you're thinking?
Yeah, or like just do in situ measurements, like you would send sort of laser beams through your interferometer, right, from one point to another, and basically ask, is my geometry sufficient?
But they have to be coming from somewhere to make sure there's this angle, because you're using your angle is your signal, right? It's unlike a digital frequency, that's your signal. This is your angular resolution. This has to be the one that's detecting gravitational wave. So you have to have some reference for you to compare. Otherwise, I would say, when I see something.
Well, so, okay, good. So actually, you could use 2 or 3 stars for that as well, right? So basically, it's good. It's like basically saying, I'm going to look at this star, and I'm going to use that star as my center, right? And then I'm basically asking, is another star moving relative to that, or another star moving relative to that?
Those stars will also be subject to gravitational waves, I guess.
But indeed, so this is like a lot like the pulsar timing array folks, right? Where you have a specific quadrupolar thing that you're looking for.
Yes, okay.
And that is what you'd see.
So you have to see a sort of stellar pattern.
Exactly.
Yeah.
Yes.
Okay,
yes,
thank you.
Yes, yeah.
So if you go back to the previous slide, you still have the sort of the diffraction limited scaling in your sort of resolution. Clearly, that should benefit from the super resolution techniques that are now.
Yeah. I mean, I've actually read some of these papers, and I think indeed, if someone can actually make that work, it would be better.
Okay, maybe we can check.
Yeah.
So nice talk. On the asteroid idea, I mean, so you mentioned the heat and the water melting and so forth. So if you have thermal expansion, you know, like even a meter of material changes by a degree of a part in 10 to the 6 or something.
Right.
So that's going to go over 0.1 micron pretty quickly, right? So
Good. So great. So the thing about thermal expansion by itself, right, is that it always happens at exactly the same frequency, which is the rotation rate of the thing. So that is not what we're looking at. We're looking at much lower frequencies. So that by itself wouldn't be a problem. Okay. Another thing we thought about is also that essentially, you know, when you think about stuff like heating and cooling, you know, the heat will only have like a few hours to percolate down. So in principle, one could even think about like drilling a little bit, like a meter or so, and then using that as your sample point. But I don't think it's really necessary, because I think basically, you know, the thing is, the complicated question here is essentially on that surface, what really happens, right? So, you know, the expansion contraction is very, you know, it's sort of very highly deterministic, right? So that happens at a very specific frequency, the rotation rate of the asteroid, and not at lower frequency.
But I mean, related to that,
Yeah.
I guess, so first of all, there's like the orbit of the asteroid, which is going to be more on the time scale of...
That's more like 10 to the minus 7 hertz or lower.
Yeah, but so now that's going to change the thermal cycling, presumably, and there's also sunspots, and I mean like...
So we did look at intensity fluctuations from the sun.
Yeah.
Okay, those are okay. It's sort of more that indeed, like, you know, so what's true, right, is basically that we're looking at frequencies above 10 to the minus 6 hertz. So the asteroid rotation, all of that happens at 10 to the minus, you know, several year time scales. Like 10 to the minus.
But the thermal heating is going to be changing over the course of that, right? I mean, it's not going to be
But it still
entirely...
comes at that frequency, right?
But I mean, I'm just not sure you can say that the thermal cycle half a year from now is exact, like...
No, but I'm looking at a much higher frequency signal.
Sorry, what's a year is around 10 to the minus 7 or something like that?
Lower than that, yeah. So we're looking at above 10 to the minus 6.
Okay, yeah. But you're confident that doesn't change by enough that it...
Yeah, I mean, like, I think, you know, if it's a few years, so, you know, a year is already 1/3 of 10 to the minus 7. Yeah. And these things are even going a little bit lower than that. So it's more like 10 to the minus 8 hertz. Okay. And I'm looking at 10 to the minus, I don't know, 6, 10 to the minus 5.
I mean, of course, two asteroids, they're rotating in 3D.
Yeah.
So can you really, I mean, sort of, is it reliable when you're looking at two tumbling bodies because rotations don't commute and these kind of...
Rotations don't, so I think that comes down to whether or not you have a line of sight the entire time or not.
Well,
right, so each
I'm asking about the thermal...
Yeah, so exactly. So for each one of these things, we did in fact estimate how bad the rotation, the torques induced to these things would be. And our estimate is that that's actually okay. And that was based upon things like, you know, the more sort of direct one is the fact that the sun's intensity does fluctuate over the timescales of interest, and you can estimate how big that is, right? So the bottom line, what we want to say is that like a few kilometer style thing seems okay.
Would it help if we had 3 asteroids instead of 2? Because okay, it multiplies number of clocks, I know, but the point is, I'm still can get over the need to know the center of mass to a micron. Presumably, if you have a triangle configuration, would it help reduce the errors?
I'm not sure it's such a rapid gain. I would think it's just like a square root kind of thing. Yeah.
Okay, but it's not going to allow to reject errors better, though.
I don't think so.
Okay.
Yeah.
So it's not like...
Yeah.
Yeah, just to clarify, so we're talking about all these seismic activities and things, right? Now, if I think about a solid rock, even no internal dynamics or so, right? There's still, it's a macroscopic object at non-zero temperature. It has all these vibrational modes.
Good. Yeah.
What is that like?
Yeah. So the vibrational modes are actually an interesting point, which is a statement that these are 10-kilometer style objects. And so we're looking at like things that are much lower frequency than the lowest frequency that can be supported in there. Okay? So the deformations that you'd worry about are more like what we call plastic deformations, which are essentially the statement that like there is ice melting, which sort of slowly changes something and not the violent modes of the object.
What are these, out of curiosity, like a kilometer asteroid, like what would be a typical vibration? I don't know, the breathing mode, for instance.
Well, the speed of sound is 10 to the minus 5.
Yeah.
So, I mean, I don't remember, I mean, you can do the estimate, but it's definitely not at microhertz.
Yeah.
Yeah.
I was wondering, oh, sorry, in terms of the signal that you're expecting, is there much modeling of the power spectrum of the gravitational waves you're expecting to see?
I mean, these estimates are based simply on the fact that I'm looking for a sinusoid, that's it. So, I mean, exactly how you pull the data out of this, the gravitational wave guys have their usual stories. I don't think we have anything useful to add on that front. Who?
I mean, like, what is emitting?
Oh, yeah. So these would be like supermassive black holes. So massive, so the thing is, right, there's this huge range of things in the thing. So, like I think, I don't remember exactly what, it's 10 to the 5 solar masses, something of this kind. So generally, this would either be a few solar mass objects falling into something huge. No, good. So the reason why you can't catch it much later is because the highest frequency you emit is set by the size of the star, right? And so the bigger it is, you will merge before you get to high frequency.
I try to imagine this situation, just your clocks on this great 2 asteroids. It's just the asteroid that's big, just rock, yeah. It's rotate around their own axis, rotate around their, So just you have just 2 dots on this 2 asteroids that's rotate just somewhere. So this distance just changes periodically. So that's this rotation should be very fast. It's don't.
Yes, few hours.
Will be average. That's
Yes, few hours.
On this. Okay. Yeah. Thank you.
Yeah, sure.
Any last questions? Yeah. Oh, not cutting off easy.
In this particular ranges which you're interested in, what about the stochastic signal? Is that present?
Oh, yeah, it is there.
Is that
so
detect this?
Is what?
So, because I guess the idea is if we see the stochastic signal throughout the entire gravitational wave spectrum, we will learn something more. So
that's right, absolutely.
You will be able to see the stochastic signal.
Yeah, look, the thing is, one of the things that I would sell these days is the fact that the PTAs have seen a blue tilt in their spectrum. Okay, so now particle theorists would like to call that cosmic, I don't know what space, whatever, strings, phase transitions, whatever things people can make up. But at the end of the day, I would say that there's a very strong case at this point when you have seen a signal of this kind to want to look just above it. Okay, and the fact that it's a blue tilt would be it's interesting already, right? That these estimates were basically made based upon some astro this, astro that. We already know that when it came to LIGO, the universe was more violent in gravitational waves than people expected. PTAs also, it has been a little bit more violent than people have expected. So, I would bet that in the middle also, it's going to be a little bit more violent than people expected. And so I think that's, for me, there's a great case right now to go right above where PTAs are and ask what's going on there. Yeah.
But there must be some baseline estimates of the population of black holes that you would expect to see a stochastic signal for. So.
That's right. So I think so. This is this complicated, thorny question, right? Because there's a lot of uncertainty in those estimates, and I am actually proud of the fact that when I was an undergraduate, I took a course on probability theory in which you're supposed to do decision analysis, and you're supposed to say, here is the probability that something is going to happen, and here is the return, and then you're supposed to multiply those 2 things and see blah blah. So if you really did the honest job with LIGO about what was known then, I wrote a paper saying you are irrational to build LIGO, and it's true, right? I also learned from that probability theory is a wrong way to make decisions about bold things because the chance that you will ever succeed on anything bold is always 0. So there's a lot of uncertainty, if you will, on this thing. And so, we really, I don't think, know very much. Shimon.
So, since you said that there's motivation to go to just above pulsar timing arrays, I mean, one thing it seems like since you're limited by photon shot noise is just build really, really big arrays and telescopes to collect the photons.
Yeah.
How much gain can you get from that versus needing to do something much more extreme?
Oh, I think like, you can see this thing, right? Like essentially every order of frequency, you're going to lose like a factor of 10 in your thing. So then you would need to make something like 100 times bigger. Right.
Okay, we're out of time. Surjeet's been thoroughly grilled. Let's thank him.
Thank you.